Hello, and welcome to Lecture 3 of Geology 234, Intro to Remote Sensing. Today's lecture is going to include a remote sensing basic overview, and this might be a review with some similar material as last week, but then that'll lead into multispectral remote sensing, so we'll talk more about bands, and then we'll get into classification pixel-based and object-based. So let's begin. So on one end of the electromagnetic spectrum, we have radio waves, really long wavelength, not as powerful or high energy waves. And on the other end, we have X-ray or gamma rays. These two extremes aren't usually that important for remote sensing, but the other areas on either side of the visible spectrum are really important because we can sense those areas using the sensors that are provided for remote sensing. And I talked about platforms and sensors last week, and we'll get into more sensors this week. So besides the visible spectrum, we are also interested in the infrared part of the spectrum as well. The energy that makes it to us originates from the sun and makes it into the Earth's atmosphere and interacts with all the objects on Earth's surface. Multiple things can happen as this energy makes its way through the atmosphere or runs into some type of matter, whether it's gas or liquid or solid. So multiple things happen at this point. We have different names for these different types of events, different things that happen. Transmission means it can pass through the atmosphere. The atmospheric window, like we discussed last week, is also really good at transmitting light. If energy isn't transmitted, then it can be absorbed into an object. Many objects absorb that energy, and that's when the molecules of that substance excite and absorb that energy. So sometimes the energy returns to the source it came from, but at a different angle. A mirror, for example, can have energy bounce off of it. Energy can also be scattered, which we talked about last week. The direction of that incoming energy randomly changes, and that energy heads off into different directions. Then we have emissions, or re-radiation of energy. So something can get energy from the sun and makes that energy as part of its own matter and re-radiates it back out. It usually does as a low energy, longer wavelength. For remote sensing, we are mostly interested in the reflectance, the wavelengths that come back to the atmosphere. Again, those visible wavelengths, infrared wavelengths, can bounce off of things, reflect off of things, and get sent back from where they came from. Sometimes in remote sensing, we also measure emissions, but that's a bit outside of the scope for today's lecture. Okay, so let's talk about sensors. A sensor is the same as a camera, but a camera is more limited. Each wavelength detected by a sensor is a band. Each individual sensor can take each image in different bands, so a red image, a blue image, a green image, and measure how much reflectance there is. How much the objects that we are taking a picture of are reflecting energy in that part of the spectrum. So that's the reflectance. The sensor converts that incoming reflectance into a digital number. The scene on the right here on this slide, we're looking at remote sensing image with one band specifically. And then just looking at one band, we are only measuring brightness in that part of the spectrum. So it's going to be black and white. And if you zoom in really close to this raster, so the raster data is all remote sensing data, ends up as rasters, then you get a grid of pixels that correspond to how much light is being reflected in that part of the spectrum. So a white pixel here has a lot of reflectance of light, and a dark pixel is not reflecting that much light in that part of the spectrum. The resulting raster has a range of radiance values. That's the brightness within the range of wavelengths within the EMS. So usually these are coded to range between 0 and 255. 0 is black, which means there is no reflectance at all. And there is absorption in that part of the spectrum. And white is the highest radiance. And that means there is a lot of reflectance in that part of the spectrum. So the number that corresponds to the reflectance in each band is called the digital number. It's a converted radiance value that takes in the amount of actual reflected light and puts it into this code of through 0 to 255. This chart here represents the bands that existed on the two last Landsat satellites that have been sent up into the atmosphere to continuously image our Earth. At the top right, we have the bands that correspond to the Landsat 8. There's 11 different bands here that all measure the reflectance or radiation in different parts of the spectrum. So band 1 is coastal aerosol, and it has wavelengths micrometers 0.43 to 0.45, and then also says the resolution in meters, which is 30. Red is another specific location in the EMS, and red consists of wavelengths from 0.64 to 0.67 micrometers. These 11 bands correspond to the areas where there's high reflectance on Earth's surface, because we want to measure those parts of the spectrum where there's a lot of reflectance. We can draw differences between different objects. So the graph on the bottom left shows the entire relevant part of the electromagnetic spectrum. This is most of the energy that makes it to the Earth's surface and is reflected or radiated back away from that surface. Those gray peaks and valleys in the back illustrate how much energy those specific wavelengths end up hitting the Earth's atmosphere. The Earth's surface ultimately being reflected away by Earth's surface. So if we go down to the far left, kind of in that visible part of the electromagnetic spectrum, 400 to 800 micrometers or so, there's a decent amount of atmospheric transmission there, and that's an important part of the visible part of the spectrum. So a lot of those bands are shown as being located in that visible part of the spectrum. So where we see bands 1, 2, 3, 4, those correspond to those wavelengths in the top right in that table. That's the range within their imaging. As we move right on this graph, we have longer wavelengths, which means lower energy radiation. In this case, these are the infrared areas, the infrared part of the spectrum. So the infrared part of the spectrum we can't see, but it doesn't make it to the Earth's surface. But it does make it to the Earth's surface and is reflected away by some objects. Plants, for instance, are really good reflectors of infrared light. It's just like plants reflect green and in the visible part of the spectrum, they also reflect red in a lot of the infrared light, the infrared part of the spectrum. And we just can't see it. So it's really important to measure infrared. And we have a couple different methods for how we measure infrared energy. So the near infrared, that band 5 in the chart at the top, near infrared, on Landsat 8, that's the reflectance that plants have. And as you get further out, even longer wavelengths, these are actually parts of the infrared parts of the spectrum where heat is being radiated back out. It's not actually anymore kind of just like the same to visible light. It's actually those longer wave infrared wavelengths that are actually heat or thermal energy. But this is a little bit outside the scope of this lecture, so we're not going to get too into thermal energy. We're going to focus more on the visible part of the spectrum and the near infrared, because these are more important in classifying things we actually see and we want to learn more about on Earth's surface. Another band worth measuring is band 8. This is called the panchromatic band, and it senses a wider range of electromagnetic energy being reflected back from Earth's surface. And because it reflects over this wider range, you can get higher resolution data from this Landsat satellite. You get 15-meter resolution data, but because it's over such a wide range, it doesn't detect colors. It just says this is the amount of light coming back. So it has a finer scale image, but it can't distinguish color with this type of band, so it's just black or white. Multispectral sensors, the sensors that we saw on the last slide, are multispectral sensors. So Landsat has multispectral sensors, so they can detect radiance or reflectance across specific wavelength ranges in the spectrum. They usually have more than one band, typically between 3 to 15 bands, or areas within the spectrum where they can detect this specific energy. Landsat 7, so the satellite that was sent up before Landsat 8, that one has there's 8 of these bands. So a multispectral sensor with red, green, blue, and then 2 different shortwave infrared parts of the spectrum. There's thermal infrared, shortwave infrared, and that black and white panchromatic band that we just talked about. With multispectral imaging, there's going to be gaps between the ranges. We don't have continuous zones, so some parts of the EMS aren't actually sensed. There are also hyperspectral sensors, which kind of fix this part of having gaps between the different bands. With the hyperspectral sensors, there's hundreds of continuous zones. The reflectance of an individual pixel is sensed in all possible colors along a continuous range of different wavelengths. However, this isn't really a feasible technology to use at these larger extents. If we are looking at actual landscapes, then we're not likely to use hyperspectral imaging. Most of these hyperspectral sensors aren't used on a daily basis. They're more for experimentation. And they're kind of overkill for Earth observation requirements or anything that we would be doing in this class. And they're slightly harder to work with as well. So let's talk about bands and composites. So each of these parts of the spectrum sensed by a multispectral sensor is referred to as a band. A sensor like Landsat 7 or 8 has 8 to 12 bands. Each band on that sensor just measures that intensity or brightness of what's sensed in that specific part of the spectrum. So the band displayed by itself will be a gray scale image. It's just black and white image. There won't be any color. So even if band 3 is red, if you just look at a band 3 alone, it will be black and white because it shows the amount of reflectance in the red part of the spectrum. So today when we do the lab, we're going to download 11 different bands and put them in Arc Pro, but each band is going to be a black and white image. So the things we see as red will show up as very bright in band 3. And things that don't have red in them will show up as very dark in band 3. Likewise, band 4 is going to be that near infrared part of the spectrum. We can't actually see this part of the spectrum, but you're going to get the brightness in the band 4 just corresponding to how much reflectance in that part of the spectrum there is. And plants reflect a lot of this near infrared energy, so plants are going to show up as very bright in band 4. However, in software like ArcGIS Pro or Envy or Adrizi, Pic4D, you can combine 3 bands at a time to make a color composite. So you can actually use tools and create a colored image, a color raster type, even though it started out as black and white. So you basically use the primary colors, red, green, and blue, to visualize each band. And when you combine these bands in this way, they appear as this colored combination between them. A combo between red, blue, and green that is visible to us. So if you take those 3 bands and put them in their corresponding RGB slots, red, green, blue, then you get a true color image, and it will just look like a photograph. It'll look like how it does in the real world, because it'll look like a photograph because the red, green, and blue are going to combine like they do in the real world. You can also portray the brightness of another band, including those other bands like the near infrared ones, as one of these primary colors, as one of these primary RGB slots, which you will get into in the lab this week. So the image on the right shows near infrared band showing up as red. So the image on the right has the infrared as displayed red. So this is Mount St. Helens in Washington State, and it has a lot of vegetation in this area, and it's showing up as red here. And why is that? Well, because vegetation really reflects the infrared part of the spectrum. The image appears mostly red. And because we have assigned the band 5, which shows the infrared part of the spectrum, as one of the primary colors. And that'll make more sense in the lab as well. So the image appears mostly red because we made near infrared look like red. There's so much reflectance in the near infrared that the image shows up as red. So this is called a false color composite. We have a true color composite, which is when we put the blue band into the blue slot, part of the remote sensing software, and the green band into the green spot, and red band into the red spot. That's a true color composite, and it'll look like a photograph that you are used to seeing. But if you mix those up and change them around, like the image on this slide, then that's called a false color composite. You are still compositing, but you are combining 3 different bands together. But it doesn't look the same way that they actually would in the real world, according to your eyes. So here's a comparison from that image from that last slide, visualized as a true color composite on the kind of top left image, and in the bottom right image, that's a false color composite. where we have the near infrared band visualized as red. This is pretty common visualization technique to draw out differences between photosynthetic vegetation. So different color composites exist to focus on drawing out differences among different types of objects. So you usually, when you see a red image like that, you normally have a near infrared band plopped in the red band. With Landsat 8, that would be a band 5, 4, 3 composite. So band 5 in the red slot, band 4 in the G green slot, and band 3 in the blue B slot for RGB. And in Landsat 7, the composite would be a 4-3-2. So inversely, band 4 in the red slot, band 3 in the green slot, and band 2 in the blue slot. But if you combine bands in different ways, you can draw out subtle differences between phenomenon that look actually pretty close when looking at a Landsat image in real life. So remember in our first lecture, I gave a use case scenario of satellite imagery that looked green for an agricultural field, and on the right you could see the infrared and where the farmer should apply more insecticide. Well, that was created using a different color composite. So that's an example of why maybe making a false color composite can be more important and useful in some cases. So there are common composite types that we use for investigating different natural phenomenons. So let's look at a couple using Landsat 7. The band numbers change when looking at Landsat 8, but for this example, we're going to look at Landsat 7. Again, all the bands are described in the top right. There are 8 different bands for Landsat 7. Blue, green, red are bands 1, 2, and 3. And so the true color composite for this type of Landsat 7 satellite would be 3, 2, 1. And then in remote sensing software, there's a slot that corresponds to red, green, and blue visualizations based on those brightness values. So if you plot band 3 into the red band 2 into the green, band 1 into the blue, then you have a true color composite, like I just stated. So you have a 3, 2, 1, which is true color composite, and that's going to look like just a basic photograph. So that's not on this slide here. But then if you do a different type of composite type, you can, and on the next slide, it'll describe some different combinations for Landsat 8. You can look up Landsat 7 composite types, but here are some listed on this slide. So if you did a 4-3-2, that's going to show peak chlorophyll. So the reflectance in band 4 shows up as red. So you can highlight different aspects of the electromagnetic spectrum using different bands into different composite types. So that red-looking image of Mount St. Helens on the last slide, that's a 4-3-2 composite, which is a false composite. That's where the near-infrared in red, the red in green, and the greens in blue. So you end up with those bright red values in the near-infrared parts of the spectrum that are really visible once you do the composite. Another example, 7-4-2, is another common band type for Landsat 7. And so here's an image, satellite image of London. This has infrared bands shown as green. So you end up with that near infrared in the green slot in that visualization software. So we'd be using ArcGIS Pro. That makes the vegetation really appear as bright green. But you actually aren't visualizing green. You're visualizing near infrared as green. With 742, if you look at band 7, you are also using shortwave infrared, which is slightly longer wavelengths than the near infrared, further away from the visual part of the spectrum. And then for Landsat 7 data, if you do 4-5-3, that's good for looking at moisture differences in soil. There's other good combinations like this that are good for looking at like urban areas or coastlines. It's fairly easy to find these lists online on USGS, other Landsat external resources. And so now, once again, it's important to note these aren't universal values here. This composite type from 321 to 453, they differ for every satellite and their bands. So if you're using a different multispectral sensor, including even Landsat 8, it will be different numbering. So true color will be a 432 instead, just like here. So I've listed on this slide for you, since it might help in this week's lab, the combinations that you can do to emphasize different aspects or issues that you want to look at. So if you wanted to really emphasize agriculture related items, then you would do 652. And so there's tons of bands that can combination types that can help you analyze satellite imagery based on your scope, the problem scope that you're wanting to analyze. So I've looked up the gisgeography.com website, and they give descriptions, natural color, color infrared, why you would want to use these certain combination types. So if you're wanting to analyze agricultural fields, you want to look at healthy vegetation that appears dark green versus bare earth, which has a magenta hue, then you would want to do this combination type. Or the USGS website, they also have lots of information on different bands and what they emphasize. So band 2 green for Landsat 4.5 is going to emphasize and be completely different than, say, Bandsat green band 3 for Landsat 8, which, well, in this case, they actually are similar, so I was wrong there, but that's not a universal rule. So they both emphasize peak vegetation, which is useful for assessing plant vigor. So you'd want to use that band. And then you could research a good combination type. And so that concludes the lecture on color composites. And now your next step is to perform the lab listed in week 3 homepage. And there will be a submittal on that. It will require 2 screenshots and answering some questions, which will be listed in the lab activity portion of the week 3 homepage.